On a chilly evening in 1935, Albert Einstein sat in his study, gazing out into the quiet night as he wrestled with the mysteries of space-time. That year, he and physicist Nathan Rosen had come up with a wild new idea: an Einstein-Rosen bridge, a cosmic shortcut connecting two distant points in the universe. It wasn't exactly a black hole, nor a wormhole as we imagine them today, but the math suggested an opening through space and time, a bridge to the unknown. For many years, scientists have wondered what lie beyond the event horizon of a black hole, and what would happen if someone was actually to go through a black hole. The concept of black holes as potential gateways to alternate universes has recently captured the attention of scientists and science enthusiasts alike. This theory, while not yet proven in actuality due to the technical limitations right now, it emerges from several fascinating areas of physics, including general relativity, quantum mechanics, and the more speculative realms of theoretical physics like string theory and the multiverse hypothesis. There are a lot of things we still do not know about the universe, but to explore the idea that black holes could be pathways to alternate universes, we need to first realize how far we have come as humanity and how much discoveries have been made in the last decade alone. Discoveries that were initially seen as science fiction or just not possible according to classical physics. But could black holes serve as cosmic doorways to other realms? We all know by now that black holes are regions of space-time where gravity is so intense that nothing, not even light, can escape from them. This gravitational force arises because of an immense concentration of mass within a tiny space, forming what is known as a singularity, where density and gravitational pull theoretically become infinite. According to Einstein's general theory of relativity, space and time are woven into a single fabric, which can be warped and bent by massive objects. In the case of black holes, this warping reaches an extreme, creating a pit in space-time. However, within general relativity, the properties of black holes become mysterious and paradoxical. The interior of a black hole is separated from our observable universe by an event horizon, a point beyond which events cannot affect an outside observer. This barrier creates conditions in which traditional laws of physics appear to break down, leading to what physicists call a singularity, or a region where our current understanding of physics becomes inadequate. Some scientists believe that rather than ending in a singularity, black holes could connect to alternate regions of the universe, which might lead to an entirely different universe altogether. So how do we know if this is even possible to begin with? One theory that supports the idea of black holes as portals to other universes involves wormholes, hypothetical passages through space-time that can connect distant regions or even separate universes. This concept of a wormhole first emerged from the work of Einstein and physicist Nathan Rosen in 1935. They proposed the Einstein-Rosen bridge, a tunnel-like structure that connects two separate points in space-time. A wormhole, in theory, would allow for a shortcut between two distant locations, functioning as a kind of cosmic tunnel. Though wormholes are purely hypothetical, physicists have shown that black holes could have structures resembling wormholes. Mathematically, certain types of black holes, especially rotating ones known as Kerr black holes, may create pathways that could theoretically avoid the singularity and emerge in another part of the universe. While no direct evidence for wormholes currently exists, their theoretical possibility aligns with the properties of black holes, suggesting they could be more complex structures than simple gravitational traps. In quantum physics, the interplay between quantum mechanics and black holes adds another layer of intrigue to the idea of alternate universes. One of the major unsolved problems in theoretical physics is the black hole information paradox, which arises from the work of Stephen Hawking. In 1974, Hawking proposed that black holes emit radiation, now called Hawking radiation, due to quantum effects near the event horizon. Over time, this radiation causes black holes to lose mass and eventually evaporate. However, if a black hole evaporates completely, all the information about the particles that fell into it would seem to be permanently lost, a violation of the principles of quantum mechanics, which states that information cannot be destroyed. To resolve this paradox, some physicists propose that information may not be lost, but instead transferred to another universe. This theory, known as holographic duality, suggests that everything happening inside a black hole might be encoded on its surface. This leads to the possibility that information crossing the event horizon could reappear in an alternate universe, accessible only through the black hole. Thus, black holes may not be dead ends, but rather bridges to other realities where this information persists in some form. The multiverse theory, which posits the existence of multiple universes beyond our observable one, has gained traction in theoretical physics. According to certain interpretations of string theory and the many worlds interpretation of quantum mechanics, every possible outcome of every event could result in the branching of a new universe, creating a near-infinite number of alternate universes. One model that connects black holes and the multiverse is the baby universe hypothesis. This theory suggests that black holes could spawn entirely new universes. When a black hole forms, it compresses matter to such an extent that it might birth a new universe inside the singularity. From the outside, we would perceive this as a black hole, but from the inside, it might appear as a universe in its own right, complete with its own space-time. Theoretical physicist Lee Smolin proposed a version of this idea called cosmological natural selection, which suggests that black holes are portals to baby universes, and that our universe might itself be the offspring of a black hole in a parent universe. The recent advancements in gravitational wave detection, including those made by the LIGO and Virgo observatories, provide insights into black hole mergers. These gravitational waves could reveal unique properties about black holes and their formation, potentially offering indirect evidence of exotic structures like wormholes. Additionally, the Event Horizon Telescope's 2019 image of the black hole in the galaxy M87 provided new insights into black hole behavior, sparking further study into their properties and possible connections to other parts of the cosmos. In 2019, humanity got its first real look at the invisible giant lurking in the center of the galaxy M87, roughly 55 million light-years away. The story of how we got that image, the dark, swirling eye of the universe's ultimate gravitational trap, is as epic as the black hole itself, involving over 200 scientists, telescopes across the globe, and a staggering amount of data. This wasn't just an image, it was a historic moment, a first glimpse into the darkest heart of our cosmos. To understand the feat, let's start with the black hole. M87's black hole is a colossal beast, with a mass estimated at 6.5 billion times that of our Sun. It's surrounded by a blazing halo of gas and dust, material being pulled ever closer to the event horizon, the point of no return. Once anything crosses this threshold, whether it's a star, a planet, or even light itself, it's gone forever, sucked into the singularity at the core of the black hole. All of this, however, is impossible to see directly. Black holes are, by definition, invisible. What we can observe is the heated material surrounding them, glowing as it spirals in at close to the speed of light. The Event Horizon Telescope, EHT project, was conceived to capture that elusive image by essentially turning the entire planet into one enormous telescope. 8 powerful radio observatories, from the Atacama Desert in Chile to the peaks of Mauna Kea in Hawaii, were linked together in an experiment requiring atomic-level precision. Capturing an image of M87's black hole from Earth was like trying to photograph a golf ball on the moon. And then came the challenge of timing. All the telescopes had to sync up perfectly to observe the black hole simultaneously, and the conditions had to be perfect at each location. Even a single cloud could ruin everything. For days, the teams waited for the stars to align, literally and figuratively. When they finally collected the data, the real work began. Each observatory had recorded information on over 1,000 hard drives, filling entire rooms. These drives had to be flown to processing centers in Boston and Bonn, where scientists could start piecing together their mosaic of space-time. The final image revealed a haunting, shadowy ring, like an eclipse frozen in time. Scientists were left stunned by the sheer beauty of it, a shadow of the black hole itself, cast by the blazing light bending around it. In the darkness of M87's core, they saw the sharp edge of the event horizon, the line where everything disappears. This was a view into the cosmos that no one had ever seen. This first image was just the beginning. It opened up new questions, new frontiers. If black holes indeed lead to alternate universes, they would not only reshape our understanding of the cosmos, but also fundamentally alter our view of reality.